This meeting is being recorded.
In section 17.5, we'll take a look at other types of aromatic compounds, including heterocyclic compounds that have other atoms besides only carbon and hydrogen. So in our review here, we know that aromatic compounds must fulfill these two criteria. So we know that they have a fully conjugated ring and an odd number of electron pairs. So another way of noting that is that they have 4n plus 2 electrons, or a Huckel's number. Then when we talk about anti-aromatic compounds, they also fulfill two criteria, the same as the first, that they have a fully conjugated ring with overlapping p orbitals, but instead of a Huckel's number of electrons and an odd number of electron pairs, they will have an even number, but we can think of that as 4n instead of 4n plus 2. So that's the main difference between our aromatic and then anti-aromatic compounds. So we can also classify compounds as non-aromatic. So again, aromatic follows these two or fills these two criteria, fully conjugated in Huckel's rule. Anti-aromatic follows the first criteria and then has an even number of pi electrons. But if a compound fails criteria 1, we consider that non-aromatic. So make sure you know the distinction between these three terms: aromatic, anti-aromatic, and then non-aromatic. So what we see here is a type of conjugated ring here, once again. These are called annulenes, and the rings are fully conjugated, so throughout the whole structure. So we have 6 annuline here, which is benzene. We have 10 annuline in the middle and 14 annuline on the end. So these could be, whether they follow those previous criteria mentioned, they could be aromatic, like benzene, or we could check them to see if they are anti-aromatic or non-aromatic, depending on the number of pi electrons. There are also aromatic rings that are carbanions or carbocations. So as long as they fill those first two criteria, then we know they will be considered aromatic. And what we see here is a 5-membered ring, which has 3 bonding molecular orbitals. So 6 pi electrons can be accommodated. And if we had 4 times n of 1, 4n plus 2, we would have 6 pi electrons. So for this a cyclopentane, right, to be aromatic, what we could have is a cyclopentadiene with a lone pair. So this is a cyclopentadienyl anion, and that lone pair is delocalized over the 5 carbon atoms, and therefore this would be considered an aromatic anion. The acidity of cyclopentadiene is attributed to the aromatic stability once it is deprotonated. So we remove this proton, its conjugate base would be this cyclopentadienyl anion that we see here. So this is, again, considered fairly acidic because of the stability of that conjugate base. As noted before, we can also have carbocations that are considered aromatic compounds. If we have a 7-membered ring, we draw the frost circle here. We see that these 3 molecular orbitals below that dotted line are our bonding molecular orbitals. We can hold 6 pi electrons. Once again, 4n plus 2. If n was 1, that would give us a Huckel's number of pi electrons. So we could have a cationic empty p orbital in this structure here, and this is called a tropylium cation, and this would be considered an aromatic cation. As we saw previously, all 3 of those bonding molecular orbitals would be filled, and since we have a Huckel's number of pi electrons, this cation is considered aromatic. Now, this next slide shows us some of those aromatic heterocycles, so rings with other atoms. So we have pyridine with nitrogen and pyrrole here with nitrogen. And both of these structures are considered aromatic rings, but for different reasons. What we have here in the pyrrole structure is the lone pair on the nitrogen would be considered part of the aromatic ring, and it is located in one of these overlapping p orbitals, and it contributes to the aromaticity of pyrrole. The p orbital that is involved in the cyclic overlap in pyridine down here, that is not housing the lone pair on nitrogen. So the lone pair is actually in an sp2 hybridized orbital on the nitrogen and would not contribute to the aromatic stability of the ring. So again, both of these are considered um, to be aromatic compounds. They both have a Huckel's number of pi electrons, and depending on which orbital they are housed in, we know that again with pyridine, that lone pair does not contribute to aromaticity, but with pyrrole, it does. So it's delocalized versus localized here. So that's important to note between those two structures because the basicity will remain for, again, this is our pyridine structure here, because of that localized lone pair on this nitrogen. This would still be considered aromatic even if it were to be protonated because we would still have those 6 pi electrons. We would still have the Huckel's number. But if we protonate our pyridine structure down here, this would become non-aromatic at that point because we would no longer have that lone pair on the nitrogen that contributes to the aromatic ring. So another way to compare the electron density observed, so if those lone pair are localized or delocalized on the nitrogen, would be through an electrostatic potential map, and that's what we see here. And in the textbook, it's noted that these two maps were carefully prepared so the colors would be correlatable, but for the most part, you should never use electrostatic potential maps unless they are prepared specifically to do so for this type of comparison. But again, we see that the localized lone pair in pyridine would make that a basic compound, whereas pyrrole, much less basic because of that delocalization of that lone pair. So there are also many polycyclic compounds that we can consider to be aromatic. Some of them are mentioned here. We have naphthalene, anthracene, and phenanthrene. So all of these are considered aromatic compounds. They follow all the criteria. And we can even see a comparison of the what's referred to as the stabilization energy. So based on them being aromatic compounds, they have this increased in stability. And we can see that benzene has the highest average stabilization per ring, being that it's only one ring. But these guys are also fairly stable, and they do experience that aromatic stabilization as well. So we will continue with the next section in our next video.